So our next speaker is Haoyue, and she will speak about MV parking functions and permutation subgraphs.
Hello. First, I want to thank the organizer to provide the chance for me to have a talk. My name is Haoyue. This talk is based on the work from my PhD supervisor, Dr. Thomas Selig, and our topic is MVP parking functions and permutation subgraphs. So let's start. First, we have n parking spots from 1 to n in a one-way street, and we also have n cars from 1 to n, and each car wants to park in somewhere based on their preferences from P1 to Pn, and here we use Pi to denote the spot preferred by the car I. And each car will park based on the preference, and if the preferred spot Pj for the car J is empty, so the car J can just stay in the PJ. But if car J's preferred spot PJ is already occupied by some car I, which arrived before car J, we say the car J will park to the first available spot after the preferred spot PJ. And if all the cars can find somewhere to park, we say the P is a classical parking function. And here we use this notation to denote all the parking functions with n cars or spots in one set. Here we have one example. So here the car 1 wants to stay in spot 2, so car 1 goes spot 2, and car 2 wants to stay in spot 1, so car 2 goes spot 1. Here car 3 also wants to stay in spot 2, but the spot 2 has been occupied by car 1, so the car 3 need to continue to go to find the first empty spot, which is spot 3, so car 3 will stay in spot 3. And for car 4, because it want to stay in a spot 1, but the spot 1 is occupied by the car 2, so the car 4 will continue to go to find the first empty spot, which is spot 4, and the car 4 will stay in the spot 4. Here, because the spot 2 and spot 3 have been occupied by car 1 and car 3, so the car 4 could not disturb these two cars, so it can just go to spot 4 to stay. And here, after all the parkings, we get the final result is this. And here we use outcome map to denote the final result from our parking function to the final outcome permutation, which can be denoted by the pi 1 to pi n. Here, the index from 1 to n means the index of our parking spots from 1 to n. And here, the pi I means the final car will stay in the spot I. And based on this example, we can get the final outcome is 2, 1, 3, 4, just the sequence of all the cars. And here, we already know there are a lot of variations of the parking functions in the literature, including the talk mentioned by the Jens, which is the multi-dimensional versions. And in our talk, we just focus on the MVP parking functions, which has been introduced by Harris and co-authors in the paper. You can check for details. And the MVP parking function is same as the classical parking function because they all have the parking preference from P1 to Pn, but the difference is that here we give the priority to the later arrived car, which means if the car J has the car J's preferred spot PJ has been occupied by some car I, which arrived before the car J, so the car J will continues to stay in the spot PJ, but the car I will be bumped from the PJ to the first available spot after PJ. And here we use this notation to denote the set of all the MVP parking functions with n cars and spots. Here is one example. So the car 1 prefer the spot 2, so car 1 goes spot 2, and car 2 want to stay in spot 1, so car 1 so the car 2 go to spot 1. But the car 3 also want to stay in the spot 2, and the spot 2 has been occupied by car 1. So car 1 will be bumped from spot 2 to the first empty spot, which is spot 3. And the car 3 will continue to stay in the spot 2, so car 3 stays here. And for car 4, because it wants to stay in spot 1, but the spot 1 has been occupied by car 2, so car 2 will be bumped from spot 1 to the first empty spot, which is spot 4. And car 4 will continue to stay in the spot 1. And finally, we get the final outcome. Also, we use this outcome map to denote the final results from MVP parking function to the outcome permutation from pi 1 to pi n. And you can find when we use the same parking function 2, 1, 2, 1, we can get different outcome map between the classical and MVP parking functions. Okay, so let's go to our main goal of the talk. We want to study the fibers of MVP parking functions, of the MVP outcome map. And it means if we already know the fixed outcome permutation pi, what is the set including all the different parking function p, all belong to the MVP parking functions, which can get the same outcome permutation equal to pi. This problem has been solved in the classical parking functions. You can check the book of Stanley for details. Now we are going to represent the set of the fiber as the certain subgraphs of the inversion graph of the outcome permutation pi. So first, let us to introduce the definition of the inversion. If we know the permutation from pi 1 to pi n, and we find the index I is less than j, but the pi I is larger than pi j, we say the pair ij is an inversion. For example, here in this graph, you can find the index 1 is less than index 3, but here the pi 1 is 2 and pi 3 is 1, so 2 is larger than 1, and we say this pair ij 1, 3 is an inversion. And here we use this notation to denote all the inversions of pi together. And the definition of the inversion graph G pi is very easy, just to collect all the inversions of the graphs together, we can get the inversion graph. And here is another definition, which is one subgraph of the G pi. It means in the inversion graph, we should conform each vertex has at most one left edge, which means in the left graph, you can find there are no vertices having any left edges. And in the second graph, only the vertex vertex 3 in the column 3 has one left edge. And in the third graph, also the vertex in the column 3 has one left edge. So all these three are the subgraphs belong to the one subgraphs when G pi equal to G231. And you can find the right-hand side, this graph is not the one subgraph because the vertex in the column 3 has two left edges. But our requirement is that any vertex has at most one left edges, so this graph is not allowed. Okay, so let's go to the relationship from parking function to the one subgraphs. If we already know the parking function from P1 to Pn, how to get the corresponding one subgraph, it's very easy. We can just collect all the edges from index I to j. If we find I is less than j, but the car will finally end up in the spot j with the initial preference spot I. For example, if we know the p equal to 2 to 1 to 3, after using MVP parking functions, we can get the corresponding outcome is 3, 4, 5, 2, 1. This can be an exercise if you are interested. And when we use the MVP parking functions, we can find car 1 want to stay in spot 2, but finally it stays in the spot 5. So we need to connect one edge between spot 2 and spot 5. So here is one edge from spot 2 to spot 5. And for the car 2, initially it wants to stay in the spot 2, but finally it will stay in the spot 4. So we also need to connect one edge between spot 2 and spot 4. And so in the graph, we have one edge from spot 2 to spot 4 like this. And for other cars, they just stay in their preferred spot, so we don't need to connect any other edges again. So combine them together, we get the final one subgraph is this. Okay, so let's go to the another direction. We can get the corresponding parking functions according the one subgraphs. Here, the definition is a little complex, so we can just go to the example for details. So here, if you already know the one subgraph is like the left-hand side here, you can find there are only two left edges, 2, 4, and 2, 5. So we need to get the corresponding parking functions based on the sequence of cars from 1 to 5. And for car 1, because you can find in the row 1, the spot is 5, but it has one left edge to spot 2. So we say the preference for car 1 is finally the spot 2. And for car 2, also in the row 2, the corresponding spot is 4, but it has one left edge to the spot 2. So we say the corresponding preference for car 2 is also spot 2. And for car 3, you can find in the row 3, the corresponding spot is in the column 1, but this dot does not have any left edge. So we say the preference for this car is just the column label of its own dot. So which means the preference for the car 3 is just the spot 1. And for for car 4 and car 5, because they don't have any left edge, so we say the preference is just their column labels, which are 2 and 3. So we combine them together and expressing based on the sequence of cars, we can get a corresponding parking function, which is 2, 2, 2, 1, 2, 3, like this. But please note that there is not always the case. If we get the corresponding parking function in this map based on our one subgraph, we can make the corresponding parking function belonging to the set of fibers, which including different parking functions having the same outcome. Because here is one example. In the left side, you find this graph can get a corresponding outcome, which is 3, 2, 1. But if we using this map again, we can get the corresponding parking function is 1, 1, 1. And after we use the MVP parking function for this PS again, we can get the corresponding outcome is 3, 1, 2, not the 3, 2, 1. So this is not always the case. Okay, so let's go to our results. The first one is that if we can get the maps from the parking function to the subgraph, which means all the parking functions belonging to the set of fibers, which can get the same outcome map pi. And based on this thing, we can get a corresponding subgraph. And also, if we can get the map from subgraph to the parking functions, we can find this relationship, which means if we can get the corresponding subgraph based on the parking function P, if we use this map from subgraph to the parking function again, we can go back to the initial parking function P. So it means if we want to calculate the fiber, it is same as to determine which subgraph S can make the corresponding parking function have the same outcome map, which equal to the outcome permutation pi. And if we can find this subgraph, it is called valid. Otherwise, it is invalid. And also here, this theorem just gives the bijection between the set of fibers and the valid one subgraphs of the G prime. Here is the second result. If we find the one subgraph is valid, it should avoid this pattern, which means if we have I is less than J is less than K, and there are two edges between I and J and also between J and K, this pattern is not valid. So we need to avoid this pattern. And as a consequence, we find the corresponding upper bound of the number of the set of the fibers. Okay, so let's go to the third result. First, we want to give the definition of the horizontally separated for the subgraph, which means if in the subgraph we can find two edges, the index is ij and I prime j prime. Here we need to find the condition between j and I prime or j prime and I. Here the conditions are the j should be less than I prime or the j prime should be less than I. If we can find this corresponding graphs are satisfied with the conditions, we say they are horizontally separated. So the first graph and the second graph are horizontally separated because here j is less than I prime and j prime is less than I. But the final graph is not horizontally separated because here the j prime is larger than I, and here there are some overlaps between them. Okay, so if we find the one subgraph is horizontally separated, we say the subgraph S is valid. And as a consequence, we also get the corresponding lower bound of the number of the set of the fibers. Okay, so now we have given the representation of the MVP packing functions with the one subgraphs. Also get some things on the MVP outcome maps. Also, we try to characterize the one subgraph S, which can be valid. And here we know they should avoid this pattern. We call this pattern 3-2-1 motif. But here, Harris and co-authors also find if the outcome permutation pi can contain the pattern 3-4-1-2, there should be some invalid one subgraphs of the G pi. But we should try to figure out more details. Also here, we want to study the family of the MVP packing functions, which called Motzkin packing functions. But unfortunately, we don't have much time, so we just skip it. So if you are interested in this part, you can check our abstract or the upcoming papers for more details. Okay, that's all what I want to share in my talk. Thank you for your attention.